Okay, the next problem is number 8. They give us two functions for this, and they ask us to graph these in the same window and adjust this so you can see both of them, and then answer these questions. What are the similarities between these two functions? Okay, it turns out they have the same end behavior. You can look at the graph here, once you have the graph, and you can see that they basically become the same function as x gets really big and as x gets really small. They don't have the same x-intercepts, they don't have the same y-intercept. Nothing else is the same other than their end behavior. Now, you can move on to the next problem if you want in this video, if you're not interested in learning y. If you are interested in the y, which I think is important because it helps tie together what we're learning here, where this comes from is this. When I do the long division, I get x squared minus 2x, and I'm dividing this into the other function, which is negative x cubed plus 6x squared minus 8x minus 15. I say, what can I multiply by x squared to get negative x cubed? That's negative x. Follow through, and you get positive 2x squared, and then subtract, and you get then 4x squared. Drop down the negative 8x, and then start over. So what do I multiply by x squared to get 4x squared? That would be 4. So 4 times x squared gives 4x squared, and 4 times negative 2x gives negative 8x. And when I subtract, I get 0x, drop down the negative 15, and once again this becomes negative 15 over the divisor, x squared minus 2x. So what this means is this. It means that this original function becomes this. It becomes negative x plus 4 minus 15 over x squared minus 2x. It's exactly like having like 17 over 5 and rewriting that as 5 goes into this 3 times the remainder of 2 over the divisor. So it's exactly the same as writing an improper fraction and set it equal to a mixed fraction when we do the division. What's handy about rewriting this function like this is that when x gets big or small, this drops off, and I'm left with just this line. So what that tells me is when this thing gets big, is that when x gets big or small, this goes to 0, and I'm left with this line, so that's the end behavior. So algebraically, through long division, you can rewrite this function and show that the end behavior of this function f is going to be this line, which is called a slant asymptote in this case. Okay, the next problem gives us a 4th degree polynomial divided by a 2nd degree polynomial, so we have a rational function here. And it wants to know some things, so what are the vertical asymptotes? Vertical asymptotes occur at zeros in the denominator. So, like I said, it's helpful to graph this function and then graph the top and the bottom. Alright, so once you get it all graphed, you can look at it. So here's the original function graphed. Doesn't look like it has any zeros. And we're looking at, zeros at the top, there's the top, and then here's the bottom. So there are no zeros in the top, no zeros in the bottom. That's going to be interesting. So let's take a look at this. Vertical asymptotes. Vertical asymptotes occur at zeros at the bottom. So we're going to take a look at just the bottom. And there are no zeros. So we're going to say none. There are no vertical asymptotes. And we can look at the original function, and just make sure that there are no vertical asymptotes, which there are none. So we just say none there. Horizontal asymptotes now, since we have the degree is higher in the top than it is the bottom, we don't have many horizontal asymptotes. We might have some end behavior asymptotes, which we could do and do the long division to get, but we don't have any horizontal asymptotes. What are the x-intercepts? X-intercepts occur where y is 0. So when you plug in 0 for y, you're solving for where the top is 0, so x to the 4th plus 5. Now when you subtract 5, you can't take the even root. You would need to take the 4th root of a negative number, which you can't do. So there are none. There are no x-intercepts, and we can see that from the graph as well. The y-intercepts occur where x is 0, so there are y-intercepts. Plug in 0 for x and you get 5 over 65. Okay, this is a really good one to practice. The next one, it wants us to match these without a calculator. So do try to do this without a calculator and see if you can do it, because it shows you really understand what we've been talking about. So this function right here gives us, we know it has a vertical asymptote at 5. So we're going to look for a function that has a vertical asymptote at 5, which looks like C. And then you can click on these to enlarge them. And then we want to shift it down 1 unit. So normally for this function, the exponent's higher than the bottom is the top, so it would have a horizontal asymptote of y equals 0. This time it's shifted down 1 unit, so the horizontal asymptote of y equals negative 1. So that's going to be C. This next one has 2 vertical asymptotes, one at negative 1, one at 3. So we're going to look for that. So it could be either A or D at this point. Now you have to click on these to enlarge them and see. But I looked at, what I did is I looked at the x-intercept and the y-intercept. Turns out this one has an x-intercept, if you click on it, at 2 right there, and that's important. The x-intercept is where the top is 0, where y is 0. So the top is 0 at 2, so that's going to match up with A, because that's the x-intercept. So that's going to be A. Okay, the next one then, we know has a vertical asymptote at 1, so we're going to look for the function that has a vertical asymptote at 1, which looks like it could be either F or E at this point. And then we can tell E has an end behavior asymptote, so it's going to be F. It's got a horizontal asymptote again at the ratio of leading coefficients at y equals 2, so that's going to be F. Okay, the next one is also has horizontal or vertical asymptotes at -1 and 3. So that's going to end up being the D one. And then this one has vertical asymptote at 2, which looks like it's this one. And it also has an end behavior asymptote, so we'll say E for that one. Because the exponent's higher in the top than is the bottom, so we can do the long division and find that slant asymptote. And the last one must be B, and it's got a vertical asymptote at -1. Horizontal asymptote at ratio of the leading coefficients, which should be -4 over 2, so at -2 it's got a horizontal asymptote. So, good practice to try to do that without a calculator. Next problem gives us this function, and it wants to know the limit as x goes to infinity. As x goes to infinity, this function approaches 6. And then as x goes to -infinity, this function approaches 6 again. And then as x goes to 3 from the right, it goes up to positive infinity. And as x goes to 3 from the left, it also goes to positive infinity. Okay, I hope this helps.